So, good morning friends. In the last video session, I tried to explain how we can connect a renewable energy source, particularly PV, to the single phase grid or a three phase grid at a glance. Afterwards, I have taken one lecture on the Zoom. Student requested that to share that lecture, particularly the practical aspect of grid type renewable energy sources. So in this session, I have considered two sources. The first source that I am going to consider is a wind, and second I am going to consider as a PV. I have used a tool, that is simulation tool, known as PSIM, and me with my some PG students, we are doing the simulations on grid type PV, and we have done the simulations on the grid type wind. This is a typical example of type D system. However, if you have gone through number of articles, you might be able to know that we are having type A, type B, type C, and a type D system. In a type A system, usually we are having the induction generator based wind energy conversion system. In type B, we are having the wound rotor synchronous generator or synchronous generator based wind energy conversion system. In type C, it's a renowned concept known as DFIG, that is doubly fed induction generator based wind energy system. And in the same case, type D, we are having the permanent magnet synchronous generator based wind energy conversion system. The beauty of this type is over here, the gearbox is optional. So as the wind speed will change over here, the rotational speed of the shaft, that is equals to the speed of the generator. So in this type D, we shall go for higher number of poles of permanent magnet synchronous generator. So it's a low speed machines, and usually PMSCs are most suitable for medium power applications. Then, as it will generate the AC power, this generator will generate the AC power, we should transform that AC power into DC power, and again DC to AC for getting the constant frequency and constant voltage at the PCC, that is point of common coupling. Obviously we are having the wind turbine control system. In that case, they are generating the reference voltages and reference current from the control system at a particular omega m. This theta is useful for pitching of the blade after this hits above rated wind speed of the wind turbine. I just have a look on to one term, rated wind speed. It is the speed of the wind turbine at which the generator, means generating system, will deliver a rated power of the generator. In upcoming lectures, I shall able to discuss about the how this speed will come into the picture. So I have used the simulation tool PSIM. In that, we have developed the RPM model through the equation of RPM available in literature. It is connected with the permanent magnet synchronous generator. We are going to measure the voltage. They are the line voltages and the currents respectively. The system is connected in star. It is connected with this ABC. It is connected with the 12 plus converter. The major drawback of this model, one should go for the closed loop of this model to get the good results of DC link voltage. Then it is connected with the inverter circuit. This has been sponsored by MTech Electronics, Gandhinagar, and the hardware setup is available at the industry premises. Then this inverter is connected with the point of common coupling, and we have considered the 50 kilometer transmission line with 33 kV grid, comparatively low voltage grid compared to other. Usually today's world this 33 kV is obsolete, so either we'll go for the direct 66 kV step up transformer at the secondary side, or we shall accommodate one more transformer, because usually as far as wind farm is concerned, the individual transformers are connected and then the main substation is far away from the installation point of the wind turbine system. Before starting the same thing, I just want to observe the effect. Means the basic aim of this simulation is that if there is a fault in the grid point, suppose there is a fault over here, then how this system is behaving. So we have run these simulations from the cut-in speed to cut-out speed. Means there is a range of the turbine from cut-in to cut-out speed, and we are having all the readings with us, but for the sake of simplicity we are using the reading of 12 meter per second. Means user has to set 12 meter per second wind speed over here. Obviously at that time the pitch angle is 0 or a minimum through which it will rotate, and we will get the sinusoidal current that is penetrating into the grid, and that is our power factor. As we have mentioned that in the grid tied system it will be having the only active power injection, so roughly our power factor is unity. I beg my pardon for this cutting the scale over here. This is the time domain. So our next thing is the inverter voltage and current and DC link voltages. So these are the two DC links are available, C/2 structure, and these are the sinusoidal inverter voltages. Similarly, we are having the speed of the rotor and the RPM, theoretical RPM of the wind turbine. Now if we go for the two wind turbine that is connected in parallel and feeding the power into the same grid, and multiple wind turbine you can use for the same. So these are the grid current, that is 3 times more compared to the first case, the power factor, inverter voltage and inverter current accordingly. Now this is very important concept known as FRT or fault ride through. So by definition it is the ability of wind turbine to survive of a short duration voltage dip over here without tripping it. The same unit, often referred as low voltage, because when the fault will be there the voltage will be dropped from 1 per unit to 0.15 per unit, and this could be also known as FRT, that is fault ride through. Modern wind turbines, particularly type C and type D system, are FRT capable. If you want to modify the same thing, we need to incorporate the device known as FACT devices. Usually it is known as the STATCOM SVC. Sometimes at distribution side we may also go for the DVR, that is dynamic voltage restorer. So again we have considered the momentary fault in this case. In this case we are considering the double line to ground fault. So when there is double line to ground fault for 15 cycles and considering the fault resistance of 0.5 ohm in the present case, you may also work by considering the various values of fault resistance and repeating the same thing to check the impact of fault resistance on the fault location and the impact on the fault current. So this is what the result, the high increment of the fault current for the particular time. Obviously it will feed some amount of reactive power from the grid, and in ultimate case the power factor will be dropping off. over here, this is what the FRT, the drop in the inverter voltage, the consecutive phase is also going to be dropped. This spike shows the regaining of the voltage. Now what is that? The regaining of the voltage is after having the post-fault condition, if the fault is momentary in nature, within 3000 milliseconds, that is a particular time as per standard, the 80% voltage profile has been regained, known as FRT. So over here, that is the regain of the voltages. Now it may happen that the strike is that much high, so our relay might be tripped. So we should design this FRT topology such that it could be regained before the relay may trip. I repeat, relay may trip. Over here, see, this spike is very small. It would be regained. So regaining means reconnecting the turbines during the post-fault condition. And this is what the rise in DC link voltage during fault period. We may also measure the active power, the VAR, that is reactive power, the drop in the power factor, and in ultimate case this is your VA. Now when we are considering the VAR during the healthy condition, that might be fed by either generator or by the grid. This is the FRT effect for triple line to ground fault. See how the voltage is dropped at the inverter, and this is the same model slightly zoomed for getting the clear cut idea. These are the simulations of an inverter for constant DC voltage of 690 volts. So we try to maintain the 690 volt constant at the input of the inverter, that is shown over here. So we can test the same thing. The hardware has been tested in the industry premises at 690 volt. So our next segment is the grid tied solar photovoltaic system. In the grid tied solar photovoltaic system, it has been also developed in one of the industry by one of my student at Viral Control, Gandhinagar. So we are having the same PV lecture previously, disconnected with the boost converter and MPPT algorithm. Then we used to connect the DC load or resistance over here, and obviously with DC link capacitor. Now we may remove that resistance after checking the voltages across the PV system. We can connect the inverter, and later on it is connected with the grid. So one more concept known as the phase lock loop. As I tried to explain in the single phase grid integration lecture, we have sensed the single phase voltage and current. So it has been run by the loop known as phase lock loop, and they are generating, in that case we have used the terminology or a symbol rho. Over here we are considering the theta, and then it is given to the current control loop. The current has been sensed, and according to the novelty of this work is SVPWM, and we are generating the pulses of the inverter. So this is what the algorithm or controller. I tried to connect it with the past lectures. We are sensing at that time only VA and IA because it was a single phase system. Over here it is VA, VB, VC. Converting this ABC, both are rotating reference frame, to alpha beta, 3 phase to 2 phase quantity, and that alpha beta is going to be converting into DQ axis, and theta has been sensed. This VQ we can take it as a 0, and VD star is generating from the voltage reference. And with this phase lock loop controller, we are having the filter circuit, controllers, and the 1/s, that is the differentiator block. These are some important equations of the current control loop available in all the literatures. These are the components of the Park transformation. where VD and VQ, this VD and VQ are the component of Park transformation of the inverter output. Omega is the angular frequency of the grid. L is the inductance between grid connected inverter and the grid depending upon the length of the line, and R is the resistance between the grid type inverter and the grid itself. To test this inverter, we have connected the EC source, and that is to be fed with the grid by all the algorithm which is most suitable for the controller design. Now, the thing is that over here KP and KI, it's a PI controller. We are generating the ID star reference. Similarly, VD. VQ will try to make it 0. Over here it's a VQ. So these are the results of the grid type PV inverter. This is the Vin input voltage to the DC to DC converter. This is the output voltage. The voltage has been boosted. The maximum power is tracking. It is generated by the PV panel. This dip shows the change in radiation. At that time also the voltage will be the main constant. This is what the reference signal generated by SVPWM technique, and we are having this three-phase sinusoidal curve on the time axis. Similarly, we can generate the reference voltages for the control loop. We have selected as 275 volt as a reference. According to that, we can have a sector identification from available sectors for SVPWM, and these are the angle for the control loop. Similarly, we can generate the output signals for the SVPWM controller. So these are the output signals for the SVPWM controllers. It will be vary depending upon the changing climatic condition or change in load, and that is depending upon the specification of the inverter. Remember, SVPWM is a technique, it's not an inverter. It is used in the inverter. That technique is used in the inverter. This is the output phase voltages of the grid tied inverter, and similarly these are the phase to phase voltages for the grid tied inverter. Similarly, we are having the sinusoidal current. During that dip also, our Q axis current will be 0 and there is changing in the D axis. This minus sign indicates that we are delivering the current into the grid. And similarly, we can generate this D ampere and D reference. Our reference current is approaching towards the actual current. And similarly, we can have a 0 superimposing for IQ and IQ reference. So we are injecting only active power into the grid. And similarly, at that time also we should check about the D and Q axis of the grid. So we need to select any of the grid angle, and according to that we shall perform this simulation. Likewise, there is a voltage. So VAB is the voltage and VAG is the grid voltage. So it has been also superimposing on the same. So it is synchronization of the inverter with the grid voltage. Now at that time, what is the active power injection? So power supplied by the grid when only grid is connected to the load. So all this power supplied by the grid. Now power supply to the load when the only grid is connected to the load. Means we have segregated the same, we have disconnecting the PV. So load will be almost same. And then we are having power supplied by inverter to the load when both inverter and grid connected mode will be there. So there is change in the inverter output with the change in climatic condition. This is power supplied by the grid to the load when both inverter and grid connected to the load. So there is change in the grid power sharing. However, the load power would be delivered by the PV and grid. So there is a load demand. There is change in the load demand in this case. Then we have also done the simulation analysis by running the simulations for multiple time for a particular location known as the Ahmedabad, Gujarat. These are the data on monthly basis, and we also tested for the STC, that is standard test condition. So in this session, we tried to incorporate the various simulation analysis of grid connection of solar energy conversion system and wind energy conversion system. Hope you are all at your home. Thank you very much. Thank you for your patience listening.